My C101 students, this is the preview video for week 13. So we're in week 13, day 1, and these are the learning outcomes for week 13, day 1. I'll probably go over at least the first 3 or first 4 uh, learning outcomes. So before that, I'm gonna need to share my screen so you can see what I just showed you. All right, so these are the learning outcomes. And again, I will most likely go over the first 3 or first 4 learning outcomes in the 12 or to 14 minutes that I'm gonna have. All right, so first learning outcome is defining thermodynamics. So if you look at this, we are defining thermodynamics as the study of energy, work, and heat. All right, now you have energy. In physics or in chemistry, the way we define energy is the capacity to do work. All right, now you see that word work, then what is work then? So basically, if you apply the force, all right, you apply a force applied, and if you move an object by some distance, we say work has been done. All right, so to keep in mind that to do work, you need energy. And the last one is heat. The way we think about heat is basically the energy transferred, right? So to be more accurate, is the thermal energy transferred between two objects. At different temperature. Right? What I mean by that is basically, I would say, let's say those two have to be in contact, right? Let's say I have a solid chunk of aluminum metal here, which is at 0 degrees Celsius, right? So I'm gonna keep this in contact with another block of aluminum. Let's say the red one is at 100 degrees Celsius, right? So when they come in contact with each other, what you're gonna see is there is heat energy transferred, a thermal energy transfer between these two, and that's your heat, right? And the way we think about heat is in terms of temperature, all right? So in chemistry, what we are mostly interested in is how much heat energy is released or consumed, right? Whenever chemical change or physical change happens, we're interested in that. All right. For example, what I mean by that is, for example, if you look at these two reactions, the first one is an example of a combustion reaction where methane is reacting with oxygen to give carbon dioxide and water. All right. So now in this reaction, whenever I carry out this reaction in the lab, what I see is energy is being released to the surrounding, making it warmer. So please write down the word surrounding here. In chemistry, the way we write down that energy is released is by putting how much energy is released on the right-hand side of this chemical equation. So this reaction is telling me that 211 kilocalories energy is released, or heat energy is released from this reaction. All right. Now, whenever I say surrounding, all right, just to keep in mind, right, just an easy way to think about this is basically, let's say if I run a reaction in a box, I'm going to run that reaction that I just showed you. It's going to happen in this box. All right. Then this is going to be called my system where the reaction is happening. Everything else around it, which I'm going to show by red thing, everything else around it is going to be your surrounding. So that means in an exothermic reaction, right, energy is released to the surrounding, making it warmer. Meaning the first example, where energy is released is an example of an exothermic reaction. All right, the next one is where the energy is absorbed from the surrounding, making it cooler, right? So this is an example of an endothermic change or endothermic reaction. And the way scientists write that down is by putting the energy on the reactant side. So that means it's telling me that 22 kilocalories of energy needs to be absorbed by NH3, which is our ammonia, to break apart into N2 and H2. All right, so again, I repeat, the top one is an example of an exothermic change or exothermic reaction. The bottom one is an example of an endothermic change or endothermic reaction. All right, but again, the idea is how much heat is released, how much it is absorbed. That's all exothermic and endothermic concept is. All right, so now whenever we study how much heat is absorbed or how much heat is released or how much heat is absorbed, we call that the enthalpy of reaction. All right. So anytime someone says enthalpy of reaction, it is denoted by this delta H. Delta H. Delta always means change in, and H is enthalpy. This is just a fancy term of telling our audience how much heat is absorbed or released by a reaction. All right. So by convention, right? And I'm going to give an example. For example, if the delta H value is negative, we say that it indicates an exothermic change. So let's write that down. So if delta H is negative, delta H has a negative value, we call it an exothermic reaction. Meaning that in my earlier reaction, I could have written something like this. I had methane reacting with oxygen gas, giving me carbon dioxide plus water, right? So this is how I balance it, CO2 and 2H2O, right? Now, since we said that energy was released, right? And we say delta H value is negative, whenever energy is released, we can write this and then write down delta H for this reaction is negative 211 kilocalorie. That's how we know this is an example of an exothermic reaction. All right, in our second reaction, delta H is gonna have a positive value. When that happens, it's indicated that it's an endothermic change or reaction. In our other reaction, I could have written down something like this is our reaction of interest. And we know that this is an example of an endothermic reaction. And this is telling me that, oh, when delta H is positive, it's an endothermic reaction. That is why I can write down delta H for this reaction is equals to positive 22 kilocalories. All right. So now we're going to go through slide number 6, right? So it tells us if we burn 48 gram of methane in presence of oxygen, how much heat will be produced? So we're looking at the first reaction, right? Methane is CS4, right? So it's asking us if you burn a certain mass of CS4, how much heat will be produced, right? So think about this as some of these houses, right, where it uses gas heating is using this chemical reaction. to heat up your house or apartment. All right. So the way to think about this is basically, I'm going to go back to my reaction. So let's write that down. I have CH4 plus O2 giving me CO2 plus H2O. I'm going to write down my balanced chemical equation, right? Where I have 2 in front of oxygen and then 2 in front of water. All right. Now, what is this telling me? Is basically my delta H value, or 211 kilocalories heat is released. All right, now if you go back to my question, it's asking me if we burn 48 gram of methane. All right, so if we burn 48 gram of methane, how much heat is produced? It's what's asking me, right? Because whenever we looked at this reaction right here, all right, what this is telling me is when 1 mole of CS4 is burned in 2 moles of O2, this is the energy that's released. But the question is asking us for 48 gram. All right, so to do this, again, we're going to use the same concept, right? Data given times conversion factor equals to our answer. Sometimes you might need more than one conversion factor. All right, so data given is 48.0 gram of methane. All right, so first step I'm going to do is convert my mass of methane to moles of methane. And I use something called molar mass. If you're not familiar with this concept, make sure you revisit that. How do I get this number? Carbon's atomic weight, right, is 12. Right, so if you look at the periodic table, carbon is 12.011 AMU, right? Plus 12. Hydrogen is 1. 1 times 4 is 4. 12 plus 4 is giving me 16 grams per mole as the molar mass. So I use this conversion factor. All right, so next thing I'm going to do is I converted grams of CS4 to moles of CS4. The next thing I'm going to do, right, is what this reaction is telling me that, right, 1 mole CS4. The balanced reaction is telling me that 1 mole of CS4 can release 211 kilocalories of energy. Look at that, my mole and mole cancels out. And then my final unit is in kilocalories. All I do is I do the math. 48 times 1 times 211 divided by 16 times 1. And the unit is going to be kilocalories. That's how I get my 633 kilocalories. That means if I want 633 kilocalories of energy, I need to burn at least 48.0 gram of methane. All right. And one last slide really quick. This concept called spontaneous and non-spontaneous. All right. I'm just going to give you a layman's explanation of this. Spontaneous is basically if I place, so think about this as my top of the hill right here. That's my top of the hill or mountain. All right. So let's assume that this is all smooth. And if I place a ball here at the very top, if I just push it, right, this ball is going to go roll all the way down here. Right? I don't need to continue pushing it when it comes here, right? It just goes down. So that's called a spontaneous process. On the other hand, let's draw the same mountain. I'll try to. This is my mountain, or top of the hill is right here. This is our ground right here at the bottom, right? Now, if I place the same ball at the bottom, this is my ball right here. Well, I'm gonna place it right here. Do you think this ball will climb this mountain up to get to the top by itself? No. Yes, it could if I continuously push it, right? Over here, I need to push it. Over here, I need to push it, and so on. All right. So this second one is an example of a non-spontaneous process. All right. So I'm going to stop here, and hopefully this preview video is helpful, and you're going to have 2 to 4 questions on top hat regarding this concept.